Since velocity is relative, and velocity is distance over time, and time is relative, we have to ask, is distance also relative? We can check if distance or length is relative. Distance is length between 2 points, typically associated with velocity and the time it takes to get places. But distance itself can be represented with a static map, such that the time of measuring distance on the map would make no difference. Two houses a mile apart remain a mile apart on the map, no matter how fast you move objects on the map, or what time of day you measure it. Therefore, if we want to know the length of an object, we can make it sit still, and measure its top, and then its bottom, at different times or days, but since it's not moving, that's okay. One of the issues with length in these cases is how do you measure a length when it's moving? For instance, when you have a map that shows two houses are 1 mile apart, it doesn't matter how fast you move toy cars on the map. The distance is the same. What if you move the map around very fast? Does the distance change now? As, by the time you have a chance to move your eyes to the other end of the ruler, the location changed, including the first end, which is no longer at the first house. We found that if an object is in motion, then the two frames of reference will argue over whether or not their clocks were synchronized or not, and this causes an issue in the agreement of length measurement. So if we want to measure length, human clocks and rods will not be very useful to us. Instead, we can use the properties of light to get what we want. Light always travels at the same speed, so we don't have to worry about whether the velocity is relative. Given that, Alice and Bob set up a new experiment. Alice and Bob fix a laser pointer at the back of their trains, and a mirror at the front ends. The laser is fired across the train length, hits the mirror, and returns back to the source at the back wall. The length of the train is therefore the distance the light traveled, and the time it takes to travel is the distance divided by how fast it traveled it. So for Alice, who is stationary on the earth at the train station, the light traverses the inside of her train without the train itself moving, and so the distance the light needs to travel is the train's length twice, and its change in time can be found by dividing the twice train length by the speed of light c. Bob disagrees because to him Alice is in motion, and Bob states that to him he is motionless, and her calculations are actually his, that it took his photons twice the length of the train divided by c. But Alice knows that it is Bob that is in motion, and so Alice does the math to check what is happening here. According to Alice, when Bob's train's back end lines up with hers, it fires a photon towards the front of the train. But the train is moving in the same direction of that photon, so the photon approaching the front of the train must travel the distance of the whole train, plus the distance the train moved in that time period. Once the photon hits the mirror and starts to return to the back of the train, the distance it would have had to travel would be the length of the train. However, before it can do so, the back of the train races up to meet the light, and so the second photon travels the length of the train minus the distance the train moved in that time period. She finds that the change in time of the moving train must be gamma squared times the stationary frame of L2 over c. If Alice used the relativity equation of change in time of one frame of reference for another, and she plugs in the equations her and Bob found, then Alice comes to find that the length of a moving train is less than the length of a stationary train. When we get Bob moving at 0.866 c, Bob and his train reduce in length by a half. Bob's 2-meter-long train is now 1 meter in length as he moves. Of course, to Bob, he is normal, he is not moving, and Alice is the one that appears to be reduced in length, in the direction of her motion, by half. Einstein's discovery that the Galilean principle of relativity had a special case, due to the nature of light, demonstrated that the principle of relativity said more than just velocity is relative, and showed that it also proves that simultaneity is relative, time is relative, and distance and length are relative. Therefore, Einstein used this discovery to show that Maxwell's electrodynamics does not have a relativity problem, just a Galilean relativity problem. By involving a simple parameter, gamma, Galilean relativity becomes more powerful, and can now deal with objects moving near the speed of light. Einstein showed then that the charged particle, from its point of view, is stationary. However, the wire which appears to be moving is reduced in length, and therefore has more positive charges closer together, and therefore the wire appears to have an electric field, which interacts with the electric field of the positively charged particle, and therefore is repelled away from the wire. This solved the Maxwell-Galilean relativity problem. Just like with the Galilean principle of relativity, if you assume it to be false, then you would have to accept that every event involving velocity would have two or more causal realities, such that to one group of people, the ball was thrown backwards, and to another group of people, the ball was thrown forward. Likewise, if you assume the special theory of relativity is false, then you must accept that two or more causal realities split from the event every time an object or photon moves. Without requiring the assumptions of many worlds, special relativity answers the question of what time and length mean to moving objects, and does so without violating causality. Since causality is the one big thing we really cannot violate, then the special theory of relativity must be accepted as true. The alternative is to violate causality or to form many worlds for each and every velocity. Let us leave off with a real-life example. The sun sends out high-energy particles that move through space at near the speed of light, and upon hitting the Earth become a bunch of secondary particles, one of which is called a muon. The muon is an unstable subatomic particle, which has a mean lifetime of 2.2 microseconds. Given the short lifespan of a muon, under regular Galilean relativity, the muon would decay before it can reach the ground. However, muons reach the ground all the time. Given the distance they have to travel from creation to annihilation, from the atmosphere to the ground, the speed and lifetime of the particle is too small to survive all the way to the ground. Calculations show that it would take 6.4 microseconds at its speed to reach the ground. So how are they doing it all the time? Well, the muon is traveling at 0.99 c. So from the ground, we would see that the muon's clock is slow and is ticking to 2.2 microseconds in what to us is actually about 10 microseconds. And to the muon, it appears that the distance between the atmosphere and the ground has reduced from 2,000 meters high to 280 meters high, so it can reach the ground in 2.2 microseconds. If time dilation and length contraction were not facts about the nature of motion, then nearly all of the muons would decay in the upper atmosphere, which is not something we experience. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.